this. So, welcome to the, now this is in German, Probeklausur, yeah, in parallel and distributed computing and of summer 2024. So you have seen this exam sheet that I put in TUBS-IRMB, and this should give us an idea how the exam that will be, I believe, in 3 weeks will roughly look like. So in this is a written exam, and you have the difficult task to do programming by pen and paper in this. So one thing that is kind of a little bit a challenge is that you need to know the order of arguments and the proper names of functions, in particular MPI functions. Yeah. So OpenMP is also part of the pool of questions that can turn up, of course. Yeah. MPI, so we used a lot of MPI, so you should be familiar with MPI and how this works. So if you are confused with something, then write it anyway. Yeah. So we'll have lots of points in a question. So of course, if you make a mistake, you put your arguments in the wrong order or something is missing, then of course you don't get all the points, but you still get points if it is reasonable and I understand what you were trying to do. Yeah, so because sometimes you may forget the communicator, or for example, some of these receive functions, they expect a status object, yeah, and that's not an object, but a status. So if you forget this is of course not correct, but I will usually then understand what you would do, and then it's probably 1 point less also. So try to write stuff, but also be familiar with the functions. So this means this is an exam where you don't have, so this is a closed book exam, yeah? This is what we have to know, and then there are simple things like, you have to write readable, and you have to write and draw things in black and blue permanent ink. If somebody has problems seeing colors, please contact us. There's a kind of a joke when I taught modeling. I had the students for over 10 years. Every year somebody wrote their exam in red. I mean, it wasn't of course not the same person. But I don't know why this happens. You should have learned this in school, and I think this is even true for non-German schools, that you don't write your exams in red. Yeah, okay. And I mean not in green. We actually do the corrections in green. Yeah, and then there's all sorts of questions. Is this green or? Okay, don't make it complicated. So we'll have 90 minutes for this. And the idea is that we have a few questions. Yeah? They are not enough to pass, and these questions, now they are kind of general. I don't know, yeah, having a few different approaches, yeah, programming stuff, and a few questions. So there will be like similar to this 30 or 25 points Yeah, and each of the questions gives you just a few points. And here you can give me some prosa. By the way, did you all do the exam? Looked into it?
I didn't do, but I looked.
You looked, okay. This is always better to do than to look. Okay. So then so the questions, yeah? A, what is weak scaling? Should I just write the answers? Okay, do you guys have problems with what is weak scaling?
It's something to do with the amount of code that you can parallelize in the. I don't really remember what is the difference between just the weak and the strong.
Okay. It doesn't necessarily has to do.
Weak scaling is when the problem size grows proportionally to the number of cores.
Yeah. That's true. Yeah. So okay, I write. So and what so you have right. So you remember it's closed book then, yeah. It will be closed book. Yes. So when we look at how well we can parallelize things, yeah. So then there is of course important to distinguish between strong and weak scaling. So the weak scaling is when the amount of work increases with the amount of workers. Okay, let's just write it down. Increasing the problem size of a parallel program proportional to the number of parallel execution units, say. So this is very general. You could of course say cores or potentially also threads. So this would mean, yeah, processors are actually, let's say, cores. So it's called, why is it called weak scaling? I mean, how do you remember this? So now you want, like take anything, yeah? So you build cupboards, right? You want to build cupboards, and now you want to build twice the cupboards, and you take twice the people building cupboards. So in that sense, it's an easy task that you get an improvement, right? That you know, it will, you're increasing the work proportional to you're increasing the work proportional to the number of workers. Yeah. So then it's pretty straightforward to say then yes, we'll get a speed up compared to if we do all in a row. That's why it's weak. Yeah? It's a weak condition. The stronger condition is if you want to keep the problem size the same and you want to try to speed it up with more workers. This is a harder problem. Yeah, this is why it's called strong scaling. So, I mean, you want to build a cupboard, yeah, and you think that your what is the guy called who's building cupboards? It's the carpenter. So, okay, so one carpenter you think the carpenter is too slow, and then you hire 10 carpenters, 50 carpenters, 100 carpenters to build one cupboard. And you see, this is a much harder problem to speed this up. This will not speed up easily because they will all stand in their way. Yeah? So this is why the one is a weak condition, more work, more workers. Yeah? And the other is a harder condition, so it's a strong, the same work, more workers. Okay. This was supposed to be the easiest question. So, I guess this is a little bit harder, the number B. So there is, I mean, depends. 32 compute nodes are arranged in a hypercube network. What is the degree of the network? Here you actually have to do a little bit of calculation potentially. First of all, you have to know what is the degree of network. You have to know what is a hypercube.
Degree of network is like log of n to the least cube.
Okay, so you say this is log 2, yeah, and then how much? The compute node, so it's 32, yeah? So what would that be? Okay, if you cannot compute this, you can write this, then I probably give you 4 points. I mean, if it's difficult to do the logarithm in your head, but you can do it the other way around, right? It's 5. Yeah, so you do it the other way around. So you 2, 4, 8, 16, 20, yeah. So you see that you end up with 5. Why is this the case? So the degree in a hyper say, what's the degree of a network? I did not ask what the degree of a network is in general, but I could have asked this too. Then you would have, so it's the number of neighbors. So how many neighbors has each node? And in a hypercube, so a hypercube has neighbors as in their dimension. Yeah? Because, I mean, what is a hypercube is something like a cube is just hyper. Okay, maybe a two-dimensional. So because, why should I draw? So if you have a two-dimensional hypercube, it is, each node would only be connected to 2 other nodes. In a three-dimensional hypercube, it would be connected to 3 other. So this guy here would have a degree of 2. Right. Okay, next question. C. Now, how did you look in our lecture? What is a mutex? And how is it used? Yeah, it is. Is it the library? No, it's. I mean, it's not. It's not a library. It's also not a function. It's, if you will. I mean, there is a library that gives you, that defines a mutex.
It
Yeah.
is a functionality to avoid the race condition between two threads so that they don't access the same variable at the same time, something like this.
Yes, this is actually a good explanation. So, for example, we could. Yes, so it is for avoiding race condition. There's actually, I've not this on my sheet here, but explained it different, but this is a good point. So first of all, the name means mutual exclusion. So this is where the name is coming from, and yes, this is say this is a functionality to avoid race conditions. So I may not have answered this myself like this, because if we have this, I would have to ask again what is actually a race condition, right? So what it does? I mean, it does not. I'm just thinking whether I mean this is of course the main. I have to stand next to the microphone. This is of course the main thing. I'm just thinking whether we can also do other things than avoiding race conditions with them. The basic idea is that it regulates the exclusive access to a resource. Yeah. So if you have a the mutex is a functionality that allows you to guarantee that only one thread, or usually one thread accesses a certain resource. Yeah. So, but you have to manage this yourself. So you could say this is a regulation, or it regulates. This is not a complete sentence. Regulates mutual exclusive access to resources. So there's a second part of the question, how is it used? And I would describe it now in a practical way. Say, when a mutex, so this is not a this is a mutex. So what do? We log a mutex. A mutex is considered to be a log. So if we log it, then all processes that try to log it again are suspended. So they get stopped. Till the process that is holding the mutex, so we use the word you hold a mutex, unlocks it. So basically this is the way it works. Yeah. So before you access something, that has to be protected. You lock the mutex. Then, everybody who is accessing that resource has to lock the mutex, and if it's already locked, everybody else is stopped until the one who is holding the mutex frees the mutex. Of course, this requires a lot of discipline. Yeah, because nobody, there is no automatism that tells the other processes that they cannot also access this. The same thing. Yeah, so you as the programmer have to make sure that this works. Yeah, this is not safe in that sense. Not safe against stupidity. Okay, so I remind you, we had mutexes. We are there's also a possibility that we get program code including mutexes or other stuff here. Yeah. Okay, then question D. We can't read it anymore. Question D is, what is a NUMA machine? So what is a NUMA machine? This is digging through the lecture notes. We did not talk about this for very long, but we mentioned it. NUMA, it's an abbreviation. So it's basically non-uniform memory access. I find one thing funny, that there's always somebody who's reading the newspaper. No, it's not newspaper. No,
That's just
it's the lecture notes, right? This is the impression that I have somehow. So like. Sorry, yeah. Okay, non-uniform memory access. So this is what is this? This is a machine. Usually the machines nowadays are like this. Yeah, so that not all memory that you have is accessible at the same speed. For example, even if you look at Phoenix, yeah, so we have two. We have two processors in this, each with 10 cores, and then we have this. What is the name? There's these not the hyperlink, the quick paths. Yeah, between them. So they are both connected to their own memory bank. Yeah, and if one processor wants to access the memory bank of the other processor, it has to go through the other processor. They call this quick path because they say this is quick, and probably it is, but this is a big technological challenge. Yeah, because if you retrieve memory if you retrieve data from the memory of the other processor, you have to go through a longer path than to take it from your own. And this, of course, is in the end slower. Therefore, this is then the NUMA machine. Yeah. Machine for which access to different parts of the memory takes different amounts of time. Or can take. So recently, it's funny that so recently I read a paper on numerics, on numerical things from the 90s, from 1992, yeah, where they discussed how much time for the computation and for memory access, and they simply said, assuming that memory access is for free, yeah, which is was absolutely the way of thinking in the 90s, that floating point operations are so expensive that memory access in comparison to this doesn't count at all. So this has been completely turned upside down. Yeah, so nowadays it's more like, especially in numerical algorithms, they say floating point operations are basically for free. Yeah. Okay, 30 years ago. So this was this, and we have two more. Ah, yeah. What is the definition of a diameter of a network? Diameter of a network. Not you. What's the diameter of a network?
It's the shortest path.
The shortest path between what?
Between the nodes that are too farthest away.
Yeah, the shortest, longest. It is the shortest, longest path between two nodes. Yeah, right. So the diameter of network.
Wait, it's
Yeah.
I got the point. Like if you get two nodes, like from the if you have like I don't know, like I forgot the term in English. It's when you have like a bunch of things, a bunch of numbers together. How do you? Sorry, like a set.
Yeah. Yeah, you have a set of nodes.
Of tuples of the nodes.
Okay, so you get tuples, yeah.
And each one of those you can calculate the minimum path.
Yes.
And you get the maximum like
Of these.
of this set
Yes.
of tuples.
Yes, that's true. This is the way you can see it. Okay, I would now say it's the shortest path between the two most distant nodes. Where I hope that I basically said the same thing as you did. Other way of saying it's the shortest, longest path between nodes. Okay, we have one more left. Sorry for being so in the exam we'll try not to give too many. Of course, yeah, we are not explaining things in between, so I hope that you get through this a bit more quicker than now. The question about an atomic operation. What is an atomic operation? So this doesn't have anything to do with the Russians going crazy. Hopefully. An atomic operation, yeah. Special atomic operations. They are special atomic operations. yeah, they are kind of a little bit like if you put a mutex around them, yeah. So this is it's called atomic. I mean, it's called atomic. It doesn't have anything to do with atomic bombs because it's atomic in the old sense that an atomic cannot be split up, that an atom cannot be split. So it's an operation that cannot be disturbed by anything else because from the outside it looks like it happens instantaneously, right? So the thing is, I mean, you may be able to simulate, I mean, you are able to simulate these things if you put mutexes around them, but these operations, what we mean by them, they are hardware supported. So you need to have a specific hardware that takes care that they are not disturbed. So this is a hardware supported. By the way, nowadays graphics cards also have these things. So it's thread safe. I don't know, did we actually use the word thread safe? Probably not. What do I mean by thread safe? What could I mean by thread safe?
There is no chance that a thread will interfere in the resource that another thread is using.
Yeah, so that the threads don't get into the way of another, yeah? So they are not, this is mutual exclusive. So if they are mutually exclusive, then they are thread safe. So it's thread safe when the outcome does not depend on the order in which the threads are executed, whether one is coming first, the other coming later, or they both come at the same time. If this doesn't influence the outcome, then we call this thing thread safe. So this here is thread safe. Operation. Taking care that the involved variables are not changed by other by other threads during the operation. So these have been the prosa questions, and now we come to the more interesting stuff. So I have to apologize that in this exam I have 2 questions on CUDA and nothing on threads. So we did a little bit more on CUDA, but then on threads and OpenMP. But I have to remind you that mutexes, OpenMP, and threads were also part of the lecture, right? So don't completely think now because I did here CUDA that these other things do not appear necessarily in the exam, but we had a little bit more of CUDA, and there will certainly be a CUDA question, at least one, in the exam. Okay, let's look at what we have here. So debugging CUDA. A CUDA kernel function for adding 2 vectors is defined as follows. So this here is the global function that takes arrays of A, B, and C of type float, and then it computes an index, and then it does the addition. Okay. The function had always worked in your previous program, but in the following snippet, it does not work as expected. And here we have a main function. So we are loading double ABC, CUDA malloc managed. We load 128 the size of float. Then we do CUDA malloc managed. So I don't know why I have put here this space. So we read vector from a file, A and B, and then we do the vector addition, and then we write it out and have more code. And now what we like to have is that C is the sum of A and B, and we see that this is not the case. And now you have to explain why. So what is wrong with all of this?
What I was thinking is that first the size of the numbers.
The size of the numbers, yes.
We have 64 blocks. Each block has one thread, right?
Yes.
And so also the index, how it is defined, I remember, that was the confusion, because supposing that this function thread IDX gives one for the number one for access the first thread of each of the 64 blocks, that would mean that we would be applying the same operation in the 64 blocks, right? Because we're not
In the CUDA block. So what would this do?
Just add 64 times or it's going to get A plus B, but
Yeah.
for the first element, 64
Yes.
times.
Yes, so it will 64 times try to right. So it will only act on the first element. Yeah. So this is one of the problem. I guess there are three problems. So what the other one you also mentioned, I believe?
The index. Well,
The index.
no.
No, okay. So we had the index. So then what else?
It's the same. I don't know what I said.
No, you said something about size.
Yes, the number, because we have 128 numbers, and
Yes.
we have 64 blocks with one thread each, so it's half of the.
So yeah, right. So we would only try to apply it only to the first half. Okay. Anybody sees another problem? You?
Do we need to free the memory afterwards?
Okay, so yeah, this is in more code. Not freeing the memory would not lead to not giving the right result, right?
Also, they're defined as double.
Yes,
The
yes.
size of those.
So right, so we got these guys here wrong. We got this here wrong. So, okay, there's again a question for an explanation. I'll now use mine. So the function add vector, I wrote it there. So add vector, as you said, is called with 64 blocks and one thread. So this is of course the problem, because the index is computed from the threads number alone, which by the way is a bad style, but is the one that was chosen here. So this is one of the problems. So we'll always get the first. Okay, we could write this here. So this is one thing. Then the next thing is that the size of the data is 128, but only 64 instances are created. And the last thing is that these vectors are defined as double while floats are expected. Actually, this would mean that the code doesn't compile even. Yeah. So now, I hope this is everything that we needed to find as problems. Then the second question is how to do it correctly. Explain how it can be corrected without changing the function at vector. So we have to replace the declaration with float star A, B, and C, and then replace the function call, or let's say the kernel call, with, okay, let me see, we don't have all of that always at the same, so we'll have to, okay, I write it from here. We have here add vector. So if you ever wonder or I already said this, how is this thing called? Triple chevron. Triple chevron. Okay, what should I write?
1 and 128.
Closing triple chevron, and then it's just ABC, right? A, B, C. Okay? Everybody agrees with the solution? Okay, is this difficult? We'll see. Sometimes surprising what comes out of the exams.
I have a question.
Yeah, please.
So the index is called thread idx.x, but then
Yes.
In the first case, then it does access just the first element, right? So if
Yes.
we have one thread, it's 164 times, right?
Yes.
Okay.
Yeah, it will be one because all of the blocks have just one thread, and we are accessing the index just from the thread. So what we should usually do is taking the number of threads per block times the block index. In addition to this, so then we are flexible in how to call the function. But because we were lazy in implementing the function like this, now we have to be careful how we call it.
Just to add to that, if we select add vector as 2, 64, that means 2 blocks and 64 threads in each block, then
So the thing here was without changing the function.
yeah,
Yeah?
so we have to change the function then we integrate the block ID and so on. Right?
Yes, so if you change the function, you are more flexible in how you call. I mean, if you change the function to use the block ID times the number of the block size times the block size plus the thread ID, then you are actually completely flexible in how to call it. Yeah, so you could also call it this way with the blocks, or you could distribute between calling with blocks and calling with threads. The thing, okay, did we discuss this we did not discuss it in very much detail, but these numbers are limited, so you can only have 1024 threads in one block, for example. Yeah. So then, if you want to have more, you have to have more blocks. And I believe, I'm not completely sure, but I believe that doing it this way is, generating a lot of blocks with one thread each is potentially not good from a hardware perspective, because I believe it would mean that each of the multiprocessors run only with one thread each. Yeah, so that you are not using it actually in very much in parallel. They have multiple. Okay, so you are using the multiprocessors in parallel, but of each of them, you would only use only one entrance in the vector unit, which is of course much slower. 32 times slower, because you are not using the vector, you are only using you would only distribute over the multiprocessors. But so the multiprocessors is like we didn't discuss this in a lot of detail. So they will have several vector units. Each of them can process one warp, 32 of them at the same time, and not doing anything else. Yeah? So it would be useful if you could put the number of threads something that is divisible by 32. Yeah, so then you would use your multiprocessors in an optimal way. Okay, let's go to the fun question. So I will always have something that has nothing to do with programming in my exam. Tea. Who loves tea? A tea collector needs an hour to harvest one basket full of tea leaves. Each basket has to be weighed on a scale, and the weight has to be recorded, which takes 1 minute. You own 6 acres, so you're an owner of the thing. You own 6 acres of tea fields, and you expect a harvest of 6 tons, the equivalent of 6,000 baskets full. Suppose you can hire as many workers as you like, but you have only one scale. Okay, so worker is cheap and scale is expensive. This is a low-income country, obviously. So now in this thing, what is the maximal theoretical speed up for the harvest compared to a single worker if arbitrary many workers can be hired? First question, is this strong or weak? Is it strong? Yeah, that is strong because you have a fixed number of fields. Yeah, so we already know that there will be 6,000 baskets. Okay, so if it is strong, then what law would apply? What does the lecture note say? Amdahl's law, yes. So, we are talking about the speed up. According to Amdahl's law. So how does Amdahl's law look like? I write a capital S to distinguish it from other S's that we may have. So it's the time that doing everything in serial would take divided by the optimal parallelization. So this can further be written with now small s. Small s is the part of the work that has to be done in serial, plus the work that can be done in parallel, but is not done in parallel because we are looking at the serial time, and then we have the serial part plus the parallel part divided by the number of workers, n. Yeah, so this is how this thing looked like. So, and then the maximal speed up is obtained from the limit for n going to infinity, so infinitely many workers, on S, which if you make this infinitely many workers, then you will obviously have S plus P divided by S. Right? So this is hopefully something that you find in the lecture notes. Now you have to make a decision. What is what? So what is S? The way. How long does this take? 1 minute. 1 minute.
So 60 seconds.
Yeah. I make a suggestion that because everything is given in minutes, suggest we do the calculation in minutes. Because you don't get a calculator. So weighing takes 1 minute. Everybody agrees.
So it's 1 minute per
Basket.
basket.
So how many baskets?
6,000 baskets.
So we'll have 6,000 baskets times 1 minute. Okay. How long to get a basket? 60 minutes. So So how long does it take to collect all the tea for one person?
6 hours.
Hmm?
1 hour it needs. A tea collector needs an hour.
Okay, now you're kind of several people are talking at the same time.
Oh, you said that how much time it takes to fill a basket?
Okay, so basically I want to fill in this, I don't want to fill the basket, but I want to fill this equation. Yeah? So it's the parallelizable part that is not done in parallel. So if you have one worker, you have to do everything yourself. How long will it take you to collect all your tea?
6,000 minutes.
So it will take you 6,000 times 60 minutes, right? So, and this is divided by S. So what is S? We have already found that this is 6,000 times 1 minute. So, now you have to do this amazing calculation in your head, okay? No computer is allowed. Which will give you what? 61, right? So you can speed up your tea collection by a factor 61 if you have infinitely many workers.
Can we bring calculators to the...
No.
No, not even like the...
Okay, I will allow you using what is this called? No, these things with the beads. What is this? Abacus. And I will allow this, or what is the English word for this? This Rechenschieber. So you can take abacus for addition and Rechenschieber for multiplication. Yeah.
What is this?
You don't know. So
Scale or something?
So this is these rulers that you can. Don't you know this?
No.
In which century were you born? In that century, okay.
I have calculators.
So what are you guys going to do if we have a when Putin comes and we have nuclear winter? No.
No, but there is like
Okay.
I don't know, like doing paper and
Okay. There's another possibility to do calculation on paper, but you can use. I allow you to use abacus and this. What is the word for this thing in English?
I guess it's just abacus.
No, the slider. You know, you have a ruler. You have a ruler with a logarithmic scale. Yeah. So you have two rulers with a logarithmic scale, and then you move one ruler against the other. Yeah. And because it's logarithmic. If for example here you have 2, and here you look at say 3, then this will line up with 6, because both are in logarithmic scale. Because if you add logarithmic numbers, you will have the multiplication.
I don't remember seeing this in my life.
Maybe
You're just too young.
it's not that famous in English speaking world, maybe.
I think it has been. So what is the name? What did you find out? Slide rule. Okay. Okay, I know when we are teaching parallel programming, we 61. This is doable. Right. So this was question 1. What is question 2? How long will the harvest take at least? So now there are different ways of answering this question, apparently. So, do I get any suggestion from you? How would you answer this question?
Get how much time one processor needs and divide by 61.
Yes. Okay. So okay. What would that be? So this is T.
S plus E divided by 61.
So this is
Adjust.
S plus P divided by 61. So okay, what would S plus P divided by 61 is obviously 6,000, right? 6,000 minutes. Okay, agree? Or do you need a calculator?
I'll just check it. But I think you can, in this case, you can just, because it's 6,000 times 6.
You can use some algebra.
Yeah, makes sense.
Yeah, okay.
You can just simplify the equation.
Yes, okay, you simplify the equations. Or you come to my computer algebra class and then you're still not allowed to use. In the computer algebra exam, you're allowed to use a computer under my supervision. We are a little slow, but it doesn't matter. We don't have an exercise. Okay, is this correct? Maybe 4 points. I guess I give you 4 points for this. So,
Yes, like the S is the parallel.
I mean, this is the, you see, this is, let's say this is the asymptotic solution. Yeah, it will be less than that. I mean, no, okay, it will be more than that, yeah? So it's asymptotic because we did the limits. We did the limit to infinity, and while doing this, I mean, okay, that would be okay, but we stepped, but the Amdahl's law does a simplification here, yeah? Not taking into account that we cannot split up the baskets infinitely. So what would actually be happening? I mean, if you do it like this, so this 6,000 minutes is only the time that you need for weighing the stuff, right?
For what?
For weighing, putting the baskets on the scale. So putting a basket on the scale takes 1 minute. Yeah? So if you start right away putting your baskets on the scale, it will take you 6,000 minutes to go through everything. Right?
Yeah.
So, but how do you start from the beginning putting the baskets on the scale? So it's not possible, because first you have to fill a basket. You cannot start weighing. You first have to collect. Right? So what you actually would have to do is to collect one bar. So if everybody starts collecting tea, they all will need 1 hour to collect their tea, and then they start weighing, right? So the real solution, I mean, the thing what I want to mention here is that this is an idealized idea. So it's an asymptotic solution. But in reality, would be like that it takes 6,000 minutes weighing plus the 60 minutes to actually collect the T. Yeah, so the reality will be slower than the asymptotic solution that you have. Yeah? Because first you have to fill the basket. Okay, there's always a difference between the idealized thing and the reality. There will certainly be a question of this kind. Yeah, so we call this creativity questions. Yeah. Okay, any questions regarding this?
There, just in the the second solution, wouldn't it be 60 times 6,000? Because if it's asked.
No, not 60 times 6,000. It will be 6,060 minutes.
But that's just the thing that I have a problem with is that 6,000 minutes is for waiting all the.
Yes.
And these 60 minutes is for collecting just one.
Yeah, so if everybody collects T. Okay, so there's of course, so there's the question, how much can you split up your thing? I mean, you could also take, we could also do it even more complicated and taking more baskets, but then the baskets would not be full, right? And then it would take longer to weigh them. So the idea, or I mean, this assumption up here would be, I mean, this is, so you could argue with me that this answer here is already correct because now in this case there are, I mean, this is not really correct because it's reality, but suppose several people could somehow manage to fill a single basket. Say when two people go through the fields collecting tea, they could potentially do it in half the time. Yeah, but you will never be able to have 100 people collecting one basket and speeding this up. So my idea would be one person can collect. So one person is filling one basket. Yeah. So this here is the absolute minimum where you can have 1,000 people filling the basket in 1 second or less, yeah, and then putting it on the scale without the consideration that they would kind of obstruct themselves or each other. Yeah, so there's a little bit of reality check in this, and for this reason, the answer here is not necessarily completely unique. Yeah, so you have a little bit to argue why it is like this. Yeah, so if you want the last point, if you want to have all 10 points, you have to give a reasonable solution that fits with the reality. Yeah, if you're fine with 9 points, I would accept this answer according to the Amdahl's law. Okay, so a little bit creativity in this thing. Okay, coming to something that has to do with OpenMP. And this is about the global maximum. Okay, in the following snippet of an MPI, program the result of a simulation, double local results should be normalized to double local result normalized by dividing it by double global maximum. Complete the snippet with the proper MPI call. Okay, so now we have here the snippet and we have a gap in the snippet. And I did something strange here. So, okay, what do we have? Yeah, we are loading, we are doing the usual stuff, MPI init, int rank size, com rank, com size. We put this in rank and size. Local result, fancy simulation, called with rank. Global maximum, we initialized by 0. And local result normalized, we initialize this by 0. Here we are supposed to write the MPI call. And already what we have here is the computation of local result normalized is done by local result divided by global maximum, yeah, and then we have the output. And then we would, now you could argue we'll also have to call MPI finalize, yeah, so this is missing here, yeah. I don't know whether MPI finalize, yeah, okay. So this would be better if I had written this. So now we need to have an MPI code in between. So how are we going to do this?
Here I have a question. Because,
Yeah.
because you mentioned that we were not allowed to use MPI functions in the exam, right? So we would, for example...
No. You have to have...
No, what I was trying to say is, for example, there are two ways. One way would be calling the operation function of MPI that gathers everything. And there's one called MPI max, I guess, that would get the maximum number of each of the...
There.
Okay.
Is that what it is?
So okay, so you mean the question that you're asking is whether I'm allowing you to use functions that we did not use in the lecture.
I guess we did use it in the lecture, but for adding numbers, not for getting the... So the command or the function is MPI, I guess it's OP or operation, and it's in the slides.
Yeah.
And one of the parameters that can be given is the operation that we want. It can be adding, subtracting. One of them, I guess.
Yeah. So we had this in the lecture. Yes.
Yes.
So what is then your problem?
If I write, because I remember that you mentioned that we were not allowed to use these type of functions, and we had to write everything.
When did I say this?
In one of the lectures I asked.
No, I guess. So I believe we had an example where I said do this without this function, right? But if I want to exclude a specific function, and I believe there is an example, right, of this in the next question. So I will tell you not to use this function. Yeah. Now here you can, of course, there are now several solutions to do this thing here. So because you can simulate each of the functions, you can always use send and receive. Yeah. So if you've forgotten everything, okay. So at least you should know what is send and receive. Now from send and receive, you would usually be able to reconstruct everything if you write the appropriate program. Unless, of course, I'm asking for a specific function to be used, which I could also do. Right? So now here you are free to do it as you wish. So in principle, Now, if you don't know the functionality, you could come and say, let's just use send and receive and write a program that is figuring out what is the minimum, yeah, and sending them and distributing them to everybody, yeah. So then you have to ask, is this enough space and to do this? I mean, you can do it. So now, since I did not exclude any particular function, it would be more useful to use the simplest one, yeah, that you can use for this. So what would be the simplest one?
I can think of two ways.
Yeah, so
One
then,
is sending and receiving, and the other is broadcasting. But the first one
how do you solve this problem with broadcasting?
you can just broadcast like every value of every node, and then
Okay.
everybody calculates, but this will just explode the number of.
Yeah, this is not very parallel. I mean, it's parallel, but it's
Yeah. It would be better, but you would kind of depend on one of the nodes to do this.
yes,
Transmit everything to the node 0.
yes.
Node 0 calculates and transmit back.
Okay, so you could collect everything at node 0, then you do the minimum there, then you send it back to everybody by broadcast. Yeah, there's a possibility.
Simply use MPI all reduce.
Or reduce.
Combine all.
Right, so this seems to be the better. Why not reduce? Why all reduce?
Yeah, reduce.
Okay, so you want to use, okay, now, reduce or, okay, so give me a hand. Who's for reduce? Who's for all reduce?
So if it's all reduced, each of the nodes is going to get the information.
Yes.
And
So, and if it is reduce, it will only the roots will get the information. So now the question is, who needs it?
all of them, because
All of them, yes. So this is why we need all reduce, okay? So, MPI, so MPI is using this, this thing that's called snake case, yeah? MPI all reduce. So, okay, so now, unfortunately, this is something that you have to memorize. But they are usually similar. These things are usually similar in what they take. Yeah? So what comes first?
Send buffer.
The sense, yes. So we'll get this by reference, because this is, let me see, where's the send buffer? What is the send buffer?
global maximum values.
This is, no, the send buffer is local result. The send buffer is local result, and this is not a vector. This is why we have to put it in, call it in by reference. So local result. Okay. By the way, I just noticed this is different in CUDA. So in CUDA there's destination, and then there is source. And here is source, and then destination. So annoying, right? So, okay, source, destination. I'm terribly bad in writing these end signs. So, where do we want to have stuff?
Local user node.
Global,
Okay.
global maximum. Okay, so then usually what comes next is
Looks like it's MPI. MPI int?
no, there's something that always comes first.
Count.
The count. The count is always coming first. So, right? So sit down, look at these functions inside one system. Like inside CUDA, they are always similar. Inside MPI, they are always similar. They may not have the same order between the two. Yeah. Also remember, MPI using the snake case, CUDA using camel case. Yeah. So without underscore and larger letters inside. Yeah. Get this into your memory because this is something that we need. So this always here we'll have the count first, and then we'll have the thing that we sent, and this is here. This is a double. So inside, well, I have to write this in all caps. Also remember this thing. These things which are indicators of, let's say, this is a constant. They're saying, okay, this is MPI double. So they are always in MPI. They are always camel case and all caps. Yeah. Whereas in CUDA they are not all caps, but sorry. They are in snake case all caps. Well, they are in camel case in CUDA, for example. So, double. Now we need, the next thing is the function. Which is the function? What are we looking for? MPI max. Yeah? And as I just said, if you do not remember, snake case, all caps. Yeah? Snake case, all caps. So, and then what we always need? Communicator. Yeah? Always remember, snake case, all caps, MPI, com world. So, and that's it. In principle, pretty straightforward 10 points, because this is all we need to do. You can also write the entire program yourself. Okay, any questions regarding this question? Then we come to the next one. So, broadcast. So this is basically related to what we just had. You want to run the following code snippet on a machine where the implementation of MPI bcast has a bug and should be avoided for safety reasons. Now, comment out MPI bcast and implement the same functionality with other functions. Okay? As here our exercise. So this is a program that is supposed to work. So we'll get MPI init, int rank. We set the rank, we set the size, we have some data. And if the rank is 0, we put data, we put the outcome of fancy function into data, and then we want to broadcast this. And then we have more fancy code afterwards. Okay. Now we want to get rid of bcasts. So I'll tell you, you get 1 point. You get 1 point for setting the command. Okay? Otherwise, otherwise I have to withdraw points if you forget this. So how do we implement I mean, now it's basically it's your turn, yeah. So if you do send and receive, just send and receive. Yes, you, because you've made the suggestion. We can do it by send and receive instead of broadcast. So what do we have to do?
MPI,
Okay, MPI,
send, underline send.
MPI send. Should I write MPI send here?
I guess, underline send.
Underline
As
send. Okay.
There is like I send to.
Yeah, okay, we can also use I send, but let's say let's do send. I think I have to write the S with capital, right?
S is capital.
I have to. This is not beautiful, yeah. So, but what are you going to send now? To whom are you sending?
Oh, maybe you have to do like a for loop.
Maybe we'll do a for loop. Okay, good. Good, let's do a for loop. Fortunately, I don't have the... So, what for? And we do a for loop. Do we start with the for loop?
From 0 to size. For int I equals 0. While I is less than
For int I
equals 0.
equals 0.
I don't know how to say this little thing. It's like comma and dot. How do I say it?
Semicolon.
Semicolon, right?
Yeah.
I less than size.
I less than size.
Semicolon, I plus plus. Then you can close it.
Yes, I closed it already.
Open the
Also, yeah, I opened the
other thing.
the brackets.
Yeah. You can
This
put,
I'm opening a scope. Okay.
okay. You can put if. Just that if I equals my rank, you continue, so you don't send to itself. That would make it zero. You're not sending the thing to,
Yourself.
yeah.
Yes.
I guess it's easier to do this way than to try to put the constraint on the for loop, and it's better to see.
I mean, we can. We don't have an exercise, so we can stretch the time. Yeah. So, do we want to continue this way, or do we have a different, better solution?
I have another solution.
Yeah, okay. What is your solution?
First, we would need to divide into pairs and even because we cannot send it and receive at the same time, right? We would need someone that sends, someone that receives.
Okay. So, by the way,
Can
just as a question. BBC, British Broadcast. What are we trying to replace? Broadcast. What is broadcast doing?
Sending information to all of them, right?
Yeah.
And just the first one.
Just one is sending to everybody. So, and that one should not send to itself. Okay, I get. Good. So, why do we want to have pairs not receiving and...
Yes, because no.
Okay, no, good. So, then what instead?
It should start from int I is equal to 1 to
So say,
I is equal to 1.
so if I is equal to 1, right?
No, I'm saying for int I is equal to 1.
So int I is equal to 1, okay? Yes?
I usually forget.
Then we receive, and for the process 0, we send.
If
The
rank-
process 0. So how do we...
If rank equals to 0,
So if rank equals to 0.
we receive. Otherwise, we send.
We send.
Send and
So if rank is equal to 0, I'm opening a bracket. Yeah? So, and then, what are we doing? So what is the rank equal to 0 doing?
Receiving.
No, it's
Sending.
It's sending.
Sending to other ranks.
At 0 cents. Because.
Broadcasting.
Okay, so what is broadcast?
15 points less.
What is the meaning of this?
I totally forgot that broadcast has this constraint that it needs you. I thought you like if any place you call it, it would send to everybody. So you need to put like if rank equals 0, like you need to constrain it from chain, but apparently it already does it internally, right?
No, the broadcast. So the broadcast decides by the so-called root argument who is sending and who is receiving.
Yeah.
Everybody who is not root, if you are root, you are sending. If you are not root, you are receiving. Yeah. So this is like, I mean, this is very philosophical. Yeah. If you are root, you don't get anything. Yeah. If you are root. What is the root and root? I don't know.
I guess now you can put the constraint in the for loop.
Why?
Why do you need constraint? He already did it.
Oh, it's already starts at 1. Okay, makes it sorry.
Why do you want? By the way, I mean, I'm horrified. I'm completely horrified what I'm hearing you here.
But
Yes, in programming, you guys listen. Yeah, whatever you can do, if you have a constraint that you could put outside of a loop. So this is really one thing that programmers always should keep in mind. Whatever you can take outside of a loop, you should take outside of a loop, not inside a loop. Yeah? Everything that goes outside the loop is always better than putting something inside the loop. As little stuff inside the loop as possible. In particular for parallel programming. I mean, if you later try to use parallelization with OpenMP, for example, yeah. So the more you can get out doing once, than instead of doing a million times. It's much better. So, of course, you can put if rank equals to 0, you can put it inside here, but this would be completely stupid. That's just burning energy, nothing else. Okay.
I
So,
think broadcast already does something like this.
so
It's because it's not. It's like negligible amount of processing, putting like comparison inside the loop, at least in this case. Because you have like maybe like 64 nodes, 128.
yeah, but
It's really
so
fast.
why would you?
It's
Why
really fast.
would you count up to 64, say, just seeing that every time you do nothing?
It's just because it's more flexible. But in this case, you can keep it like that. It's
Well, why is putting it inside more flexible than putting it outside?
You can set, for example, an integer root, and instead of passing rank equals 0, you pass the root value. So you can set any root.
I can still I can put this here too.
I'm sorry.
I can put this too. I can write here instead of 0 root.
Yes, you can. But in this case, how can you constrain the for loop? If it's not on the beginning or the end, you need to put this comparison somewhere.
So you want to say if it's in between, if the root would be in between.
Yeah. Or you make two for loops. It's also a possibility. But
Okay, so
anyways, this discussion is really
Okay, if it was somewhere in between, yes, then this would be, yeah. So then this is by the way, this is one of the reasons when you don't have any particular reason that it would be somewhere in between, you always put the root to 0. We always like the root being to 0, because if it's not 0, we run exactly in this kind of problem, that instead of asking once what the root is, you would have to ask every time what root is. Yeah, because you would have to put this inside then. Yeah, so, okay, good, thank you very much. Yeah, we just discovered that we prefer to have the rank equal to 0 because of this. By the way, when I'm looking at this, actually, what would be even better would be to put all of this inside here. This would be even better because we just have this function. But according to the question here, you should put it below here. So then this is what we are going to do. So now, yes, thank you for this lively discussion. We'll do now the MPI send. MPI send with a capital S. So we'll have the data that we have to send. So this is in here. So data. Okay, we can actually look most of these things up here, right? So we'll do data. We send 1, and we have an MPI int that we want to send. So until here we can just copy. Yeah. Now we have to. The next thing is the destination. What is the destination? The destination is I. Then we have some additional information here. We'll have a tag here, right? Which we have not specified. So what we can do is we can specify a tag, or we can write 0. When we put 0 or 1 or 255 here, the only thing that we have to remember is that the receiving part has to have the same tag, otherwise it will be not taken up. Yeah. So we put 0, then we remember that. Okay, this is the easiest way to put here 0. And then, of course, what always ends this is the communicator MPI com world. Okay, and that's it. And I'm going to close 2 of these brackets. So now we have done the sending part. Then, how is receiving working? Else, yes. Else opening brackets. Okay, we'll define. Okay, then we can define MPI status. By the way, if we do it like this and not using it, there's another option. You can write MPI status ignore. Yeah, but if you wish, we can define a status here. And then we do the receiving, right? So this is just MPI RIX. Okay, this is how it's called. And now it's pretty similar to what we had. It's data 1. It's an int, MPI int. What's next? Hmm?
0.
Which 0?
To the, like,
From the root.
Very in front.
And then what's next?
Another 0.
Another 0 for what?
Tag.
For the tag, right. So, and then we have the communicator. Yeah, and then we have the communicator first, MPI com world, and then what's next? Strange that they put it in this. So then we still have the status. And then we have to close the brackets. Okay? Or instead of this, we can write status. Oh my God, is it status ignore or MPI status ignore? I don't.
It's MPI status ignore.
MPI status ignore, right? Yes, it would be MPI status ignore. Okay. Sometimes I make my own mistakes here. Just ignore, right. Yeah, so they all start with MPI, yeah, so that would be logical that it is. I mean, if you don't remember yourself, yeah, think about it. So everything else started with MPI int, MPI com world, then it will probably also be MPI status. Okay, are we done with this?
You have to write MPI final.
Okay, so this new code here, more fancy code. So we are only supposed to. So this is going on, and I would assume that later it will take care of this. Yeah. So what was the challenge here was just to replace the broadcast. Okay. I guess we have one more. One more question, which is also related to CUDA. And by the way, I'm in the habit, so some students, so most of you are new to me, so you don't have a lot of experience with me. I have the tendency to put at the last question something where you have to write more. In a sense, this is, I later, I mean, there are different choices how you can do an exam. So I usually give more to do and then decide later on how much I was expecting. Yeah. So you can. This is a little bit my style. Yeah. So you should. This is not an invitation saying, okay, then I do only the first two. Yeah. This is not a good solution to this. Yeah. And also the experience from last time. I don't want to shock you, but last time we didn't get a good result in the exam, I have to say. Yeah, so this was, I hope you do better than they did last time. But, okay, my style is usually to end with a question that takes a little bit more time also to write, yeah? And now this is the last question of this exam. And here, the following snippet of CUDA code must be rewritten such that it runs on devices not supporting unified shared memory. And here, I ask you to rewrite the entire code. Yeah, because it is, so to speak, up to you how to put here things in between. I mean, finding the right positions where we enter new functions. Yeah. Okay, so we'll have double data, CUDA malloc managed, 1024 size of data, init data with random numbers. Then we write them out, and then we do for E. Yeah, right. Then we write them out. Then we run the simulation. Then we write them out again, and then we are writing the data out again, and then we free, and then we return 0, right? So this is the function. Now we have to rewrite the entire thing. So it's probably not enough space here, but we'll have paper after this. Yeah. Okay, so basically we start with in main didn't take any arguments, so we'll do it again with this. So basically we need everything that we had here too, but we'll need a little bit more. So obviously we'll need this double dots. So what will change if we cannot use managed memory?
First, instead malloc manage, it would be CUDA malloc.
Mm-hmm.
And we would need to send and that's where I
We'll have to send, right?
and copy.
Copy where?
On the host.
On the host. Yeah. So what is the first thing that we need?
We need to allocate memory on the host.
Yes. So what do we do before we allocate memory on the host?
We need another variable.
We need another variable, right? So we need a copy on the host. Let's call it host. Right? Okay, then we do the allocation. So this will be CUDA malloc instead of malloc managed. And then, the thing would be the same. Yeah, so it's 1024 times the size of double. Okay, and now, as you said, we also have to allocate memory on the host. Yeah, so for this we need to remember how this is done in basic C style. So basic C style, the malloc function gives a pointer to void. Yeah, because it's just taking memory. So in order to use this with the typed language, C++ or CUDA, which is typed, we have to do a casting first. Yeah? So how's the casting done? So to what do we have to cast it, by the way?
You pass a pointer of a pointer.
Yes, I cast a pointer to a pointer. But the pointer that I get is a pointer to void.
No, like the code you that is a pointer, and you pass the pointer of the pointer, or the.
You mean I take the wait?
I'm not sure if this returns your value.
Wait, because you said that that the end is wrong, because it's already a pointer. You are. Let me see. I think you are right. Maybe I made a mistake. So maybe this will improve my ratings on YouTube again, because every time we make mistakes we get more views on YouTube. Let me see. You are right. If this is a pointer, then we should already. Let me see whether I got this example and have misdone this again, but let me check.
So it's apparently you have to pass a double point. Pretty sure one.
Kudamen. Kudamen. Okay, we have it the same way in the Kuda malloc. Let me see. Now you're confusing my. So we always had. So we had it in the notes. We had it like this. That we get the reference. Because it's expecting a pointer. Yeah. Okay. Anybody Googles whether this is correct or wrong?
It's double pointer.
Hmm?
It's a double pointer.
It's a double pointer. Yeah. This is why we'll have this end anyway. Okay. Good. So then this was the correct way of doing the allocation. Right. So sorry for the confusion. So we were actually at the other thing that we did the casting, right? So what do we need to cast to? Yeah. So the malloc will give us a pointer to void. We cast it to the pointer to double, right? So we'll have this. So we have to write this in front, so to get the casting.
I think we need to write double star. It's not in front.
Double. It's not in front. It's in the back. Yes. Yes. Yeah, you're right. Sorry. Yes. So it's like this. Thank you for taking care of me. So then we do the malloc. With how many L do we write malloc? With 2. Malloc. And then it's just the size. So it's 1024 times size of integer of double size of double. So now we got what we needed. Okay, now we allocate it, and now we get the next thing that we have in the function here is init data with random numbers. Okay, and this is the kernel function. So this will init data, not data host, yeah, but we can call this init data with random numbers. So we do our triple chevron, open and close, and put here data. Okay. Then the next thing is that we want to write things out. And if we want to write things out, we can only do this from the from the host, so we'll have to do copying first. Or we can start writing out and then do the copying, but I would say we'll do the copying now. So this is CUDA memcopy. Now in CUDA, we always put the destination first and the source second. Yeah, it's a bit different from OpenMP. Wait, that's OpenMP. From MPI, it's different from MPI. So it's does the destination where we are copying to. We are copying from data. Then we have to specify how much we are sending. We are sending 1024 times the size of double. And then we have to tell them what to do. And this is done by CUDA. Yeah, always remember now this is camel case. CUDA mem copy device to hosts. Now we did the copying. After the copying, we do the write out. So this is simply something that we have to, that we can just copy from above. So this is standard namespace cout. Now this is a double chevron only. Data before simulation. Standard end line. And then we have the loop, which is for int equal to 0. This is smaller than 1024. So unfortunately, we have to do a little bit of copying now here. std. So this is a now question how good you are at copying without making mistakes. It's easy to make mistakes while copying. We got that I, and I have to put the end line in a new line, end line, and we are closing the brackets.
That's all.
Yeah, so you are so right. Okay, yes, I said we just need to copy, but you're of course right, this is not, this is that. Okay, now see, we put this on the other side. You are so right. So this is that host of I. Yeah. It's easy to make mistakes. So the next thing is to run the simulation. We don't need to change this. Run simulation. This was by 32. And this now is on the device, so it's actually that. Yeah? Now, if we want to get it out again, then we have to copy again. This is CUDA. CUDA. It's like it's exactly 12 o'clock, so I'm getting hungry. CUDA mem copy. Okay. It is exactly the same as before, right? That host, that it's 24 size of double is exactly the same, so it's again CUDA mem copy device to host. Now we have our data back. Don't forget the semicolon in the end. And so, okay, then we have to do the write out again. So it's std cout. It's the data after simulation. End line. Okay, not to get yeah. Continue. Okay, we'll put this on next page. Continue assignment 6. So we'll have just started with writing these things out. So what comes next is the for loop for int 1 e is equal to 0, I is smaller than 1024, I plus plus comes here std cout I so again, as your colleague reminded us, this is now not the data as in the code here, but it's the data on the host. I std end line. So, almost done. There's one more thing that we have to do, is we have to free that, and this means what else do we have to add?
You also need to free the data host.
I have to free the data on the host, this is semicolon, and then we'll end as we had it with return 0, and then we close. By the way, I did not close this bracket, right? So I missed one up here in the loop. And then we have to close the brackets that is related to the main function. Okay, so basically that's it. I will now stop the recording, and if there are more questions, we can discuss them offline.